Hello everyone. In this video, I will explain the experiment on diffraction grating and the determination of the wavelength of spectral lines of Mercury using the spectrometer and diffraction grating. So I will use the virtual lab, which is the open source project of Amrita Vishwa Vidyapeetham under the initiative of Ministry of Human Resource and Development for the education through ICT. I will use the virtual lab provided by Amrita Vishwa Vidyapeetham. This is the virtual lab provided by Amrita Vishwa Vidyapeetham. This is the spectrometer shown here with collimator attached with a slit at one end, and this is the telescope, and eyepiece is attached at the one end of the telescope. There is a table on which prism or grating can be mounted. Now I will focus this telescope for the distant object for parallel rays of light using rack and pinion adjustment provided here. And when you get the clear image of the distant object, this telescope is set for parallel rays of light. Now the top view of the spectrometer is shown here, and this spectrometer is attached with a main scale and vernier scale, and this main scale is circular in nature, and there are two scales opposite to one another, and they are having the difference of 180 degree. That means if one scale shows 0, another scale will show the reading of 180 degree. And here this main scale is in terms of angles, that is in terms of degree, and vernier scale is having 30 divisions, so that the main scale is divided into number of parts. Here clearly you can observe from 0 to 10 degree there are number of markings, and this 10 degree is divided into 20 parts. Therefore, the value of one part becomes equal to half degree. And if you convert that into minutes, that comes out to be 30 minutes. 2 division means 1 degree. 3 divisions means 1 degree, 30 minutes. This short division is read as 30 minutes. That is half degree. First, you have to find out what is the least count of this spectrometer using the value of one main scale division divided by total number of divisions on the vernier. Here I will show the least count of the spectrometer, and value of one main scale division is 0.5 degree. Number of divisions on the vernier is 30. Convert that into minute, that comes out to be 30 minute by 30. Therefore, the least count of the given spectrometer is 1 minute. And also you have to find out what is the grating constant to be used, and the number of lines per inch of the grating is 15,000 lines per inch. That is 15,000 slits are there in 1 inch length of the grating. Convert that into per meter by dividing it by 2.54 into 10 to the power minus 2 meter. That means 1 inch equal to 2.54 centimeter. So this is the value obtained. Therefore, the grating constant is given by reciprocal of number of lines per meter of the grating, and that gives you the value of 1.69 micrometer. 10 to the power minus 6 meter, that is micrometer. This is the grating constant that gives you the width of one slit and one opaque portion. That is A plus B, where A is the slit width, B is the separation between the successive slits. So once you get the value of least count, 1 minute, and the value of grating constant, that it comes out to be 1.69 micrometer. Now we'll go for the actual experiment. So here, first we have to set the grating for normal incidence. That means the incident light must be perpendicular to the plane of the grating. That means if grating is mounted here, so just I will show here. If grating is mounted here, the light incident on the grating must be 90 degree with respect to plane of the grating. So for that, there is a 4-step process. First, you have to rotate this telescope by 90 degree, then mount the grating and rotate the grating table slowly so that this grating is inclined at an angle of 45 degree with respect to the incident light, then you will get the reflected image in the telescope, which is perpendicular to collimator. Finally, you have to rotate this grating by 45 degree. Then exactly the plane of the grating will be normal to the incident light. That is called as normal incidence setup. So just I will show you step by step procedure. Now I will switch on the light and you will observe the slit here. You can focus the slit for clear image. I will slowly rotate this telescope so that you can observe the slit here, sharp slit in the field of view. You can focus the slit using this particular collimator rack and pinion adjustment because telescope is already set for the parallel rays of light. Now to get the good sharp image of the slit, you have to use the focusing setup given in the collimator. So just I will focus that for clear image, and slit width can be adjusted using this screw. So width of the slit must be very sharp. Now, first step, you have to focus this telescope, that is this cross wire must be directly focused to the slit. So slowly using the fine adjustment of the telescope, you focus this directly to the slit. Then I will rotate this vernier slowly so that this 0 mark comes to exact whole degree, that is whole reading, so that I can rotate this telescope by 90 degree. So slowly you rotate this and I will set this for 50 degree. And now telescope is focused to the direct slit and angle between this collimator and telescope is exactly 180 degree. If they are in a straight line, now you rotate this telescope by 90 degree. Now telescope is showing the reading of 50 degree. Now the difference must be 90 degree. So that I'll rotate this telescope by 90 degree in this direction, and 50 plus 90, that is 140. So you have to rotate this telescope slowly until you get the 0 mark of the vernier exactly matches with 140 degree. So still I will rotate this telescope slowly and 0 mark should be at 140 degree. And using the fine adjustment of the telescope, you can set it for 140 degree. So now I will use this fine adjustment. So move this to 140 degree. So let us take this as 140 degree. It is exactly not moving. So in practice, in a practical case, you have to exactly set it for 140 degree. Now you take it at as 140 degree because this telescope is not moving here further. Now what happens? This collimator is perpendicular to the telescope, 90 degree with respect to each other. Now you have to place the grating and slowly rotate the grating table or vernier table slowly so that this grating will be inclined at an angle of 45 degree. So just you have observe here, I am rotating this grating table slowly until I observe the reflected image of the slit, and you observe the field of view here. You will observe the field of view and the slit image start to appear. And now exactly focus this reflected image of the slit to the crosswire. This is the third step. And when you observe the reflected image with the collimator and telescope are perpendicular to one another, then what happens? This grating will be inclined at an angle of 45 degree with respect to incident light. Now we have to set this grating for normal incident. That means plane of the grating must be perpendicular to incident light. Now this is at 45 degree. So in the last step, what you have to do, you have to rotate this vernier disc by 45 degree. Okay. Now I will use this fine adjustment of the telescope and I will set this for exact value. So now this is 110. So on the right side we have 120. This is 100 side. It is 105, 105, 104, 103 and 102 and 30 minute. 102, 30 minute. I will set this for 102, 30 minute. This is 102, 102 degree, 102 degree and this is 30 minute. Now you have to rotate this grating in this direction, that is in anti-clockwise direction, so that this grating will be perpendicular. Okay. And now it is 102 degree. Just I will rotate this vernier disc so that I will see whether I have to increase the value. Yes, I have to increase the value. So when it is 45 at an angle of 45 degree, the reading is 102 degree, 30 minutes. Now rotate this grating table by 45 degree and I will make 4 plus 45 degree. And you should reach up to 147 degree, 30 minutes. And rotate this grating table and set this exactly to 147 degree, 30 minutes. Now this is 145 and move it further and it is 146, 147 and 30 minutes. Exactly set this. Now basically this grating becomes perpendicular to the incident light. This is called as normal incidence setup. This is the last step to set this grating for normal incidence. Now you are free to move this telescope and the position of the direct reading, that is direct incident light direction, and the diffraction of light can be studied. Now rotate the telescope and move it directly to the slit. Direct reading again you have to take. That means first you have to take and move this telescope. Now fine adjustment I will use. Move this telescope. Adjustment you can use. And directly focus to the slit. Now this is giving you the reading of incident light direction. Now note the reading here. This is 60, this is 70, this is 50 side. If you take the reading here, MS are just behind 58 degree and therefore the MSR mean scale reading is 57 degree 30 minute. That has been crossed but it is just behind 58 degree. Therefore the MSR reading is 57 degree and 30 minute. It has crossed that just behind 58 degree. And just to observe the 30 lines and identify which line is exactly coinciding with the vernier division here. And this is just about to reach 58 degree. It must be around 25 above. So exactly I can see here the 29th line is exactly coinciding. Therefore the CVD coinciding vernier division is 29. Now I will take that direct reading and I will use the formula to calculate the total reading, that is direct reading. Here I will show MSR is 57 degree 30 minute and coinciding vernier division is 29 and that has to be multiplied by least count of the spectrometer, that is 1 minute. Now this becomes 29 into 1 minute, that becomes 29 minute. So the total reading will be, you have to add minute to the minute only. So total reading will be 57 degree 59 minute, that is 30 minutes plus 29 minute, total it will be 59 minute. So that is the direct reading that gives you the direction of the incident light. Now I have to observe the spectrum shown by the diffraction grating. Because of the diffraction of light, when light falls on the grating at an angle of 90 degree, light will bend and somewhere here I will get the first order spectrum and after that you will get the second order spectrum. Just I will rotate the telescope slowly and you will observe the first order spectrum and second order spectrum on either side of the direct reading. On right side also you'll observe, on left side also you'll observe. Now we'll rotate the telescope slowly. Now you can observe the first order spectrum. Here you observe violet line, blue line, then blue-green, green and yellow lines of the Mercury. So these are the prominent lines observed for the Mercury source. If you move it further on the left side, and here in the field of view, you are observing first order spectrum. And if you move it further on the left side, you will observe the second order spectrum, and that has the lower intensity, but dispersion is more. That means the deviation of the spectral lines are more, but intensity is going to be lesser. And here you can observe the spectral lines observed in second order spectrum. Now I will take the reading in first order spectrum. Now I will focus this for violet line. Slowly, I will use the fine adjustment. Fine adjustment you have to use and focus this for violet line. Now take MSR and CVD for violet line. And this is 50. On right side we have 60, that is increasing here. This is 45, 44, and this is 43. And this 0 mark has crossed 43 degree and 30 minute. And note the coinciding division exactly. And if you observe it carefully, the coinciding division is 4. The fourth division is coinciding. If you carefully observe, the fourth division is coinciding. This is 0, 1, 2, 3, 4. Fourth division. Now I will note that reading. Now we can observe the MSR I have entered here is 43 degree 30 minute and CVD is 4. Therefore total reading related to the violet line is 43 degree 34 minute. So 30 minutes plus 4 minutes because CVD, that is least count, is 1 minute. Now I will take the reading for blue line. So using the fine adjustment of the telescope, move this to blue line and take the reading. And this is 44, 43, 42. 42 degree 30 minute. And if you observe the CVD, so that is 5. 42 degree 30 minute and CVD is 5. So I have entered the reading for blue line and the total reading is 42 degree 35 minute. Now I will move it to the other lines and I will take the reading. Now I will focus it to blue-green and note the reading here. It is 40 degree 30 minute. The CVD is 4 again. And I have taken the reading for green. And finally, I will focus this to yellow line. Crosswire is exactly matched to yellow line. And note the reading here. This is 37 degree 30 minute. And again, the coinciding division is 2. I have entered the reading for yellow line. Now I have taken the direct reading as well as the reading for 5 different lines of the Mercury, and this is the position of the telescope. And direct reading is observed here. What is this angle of deviation for different lines of the Mercury? I have to calculate. And it is observed that different wavelength is going to be deviated by different angle because of the diffraction phenomena, because the angle of diffraction mainly depends on the lambda value. So now I will calculate, I will switch over to that tabular column and I will calculate the value of angle of deviation and I will calculate the value of wavelength. Now the direct reading is 57 degree 59 minute and I will subtract this value of the reading for each line from 57 degree 59 minute, and I will enter the value of this angle of diffraction here after that calculation. So here finally I have calculated the value of angle of diffraction for all the spectral lines of Mercury. And as you go from violet to yellow, the angle of diffraction increases. And using the formula d sin theta equal to n lambda, and by taking the first order n equal to 1, and I have calculated the value of wavelength, and they are exactly matching with the standard wavelength of Mercury, and there is a small error. It may be any experimental error or the error while taking the readings. And it shows that this experiment gives you the wavelength of spectral lines of the optical source. Using this technique, you can find out the unknown wavelength of the spectral lines also. And thank you for watching and subscribe my channel. And this is the video of explanation of the experiment of determination of wavelength of Mercury lines using diffraction grating. Thank you.